Okay, let's look at the next chapter of functional programming in Lean. In this chapter, we will learn about overloading and type classes, and I want to try something a little different this time. So instead of reading word by word, I think I'll try to summarize a bit to hopefully make the video a bit less painful to watch. Okay, so many programming languages have a special treatment for like the primitive types. For example, in Java, you can use the plus sign to add like primitive numbers, but not, for example, big int numbers. And obviously, this also extends to numeric literals. And then other languages like C++ allow you to overload these operators for your own types. And of course, even languages that don't have overloading for operators or literals, they still often have overloaded functions. For example, Java. Overloaded functions are just functions that have the same name but like differ in the arguments. And the compiler then just uses the argument to pick the correct implementation to use. And well, this can happen at runtime or at compile time, I guess. And the limitation of this kind of overloading is that it doesn't compose very nicely. So if you have an overloaded function that works on strings and byte arrays and file pointers, you cannot really write another function that calls this function that works with the same type in a polymorphic way. You have to then also define overloads for the calling function, which can lead to a lot of boilerplate. And another consequence of the overloading is that if you have a very general method, for example, the equals method for objects in Java, then it's just by default, well, everything uses that general method unless you overload it, and that can then lead to bugs because instead of the compiler telling you, oh, this method doesn't exist, it's just going to call the general version, which is almost never what you want. I mean, at least in this case for comparing the equality of objects. But of course, functional languages like, for example, Haskell also support this kind of overloading, for example, of the plus operator, but they do it in a way that is that works much more nicely with parametric polymorphism, aka generics, and it works by defining something called a type class that then contains a collection of these overloadable operations, for example, like the plus operator, and then you create instances of this type class for your types. For example, you create an instance of add for the natural numbers. And this way you get this kind of ad hoc polymorphism, like overloading, where when you write a plus in your code, the compiler knows which implementation of plus to call, but it also works very nicely with your generic code because you can then use the type class to specify the constraints of which overloads essentially you need to be available for your generic function to be callable. Yeah, and the terminology here is really confusing. So, well, at least if you're coming from object-oriented languages, because the keyword for this is class, and you call a definition of such an overload for a particular type, you call an instance, but obviously that's not how you would use the words class and instance in OOP. So that's why, for example, in Rust, I think they have a really good terminology for it because a type class is just called a trait in Rust, and an instance of a type class is called, well, an impl trait, so an implementation of the trait. And I think actually those are much better terms for it, but I guess in Lean they also use the class and instance terminology from Haskell. And I mean, if you think like purely semantically about what a class is, it's just a group of things that share some common attributes, right? But so it's not like it's the wrong term. I just think it's confusing because that term has already taken on a different meaning in object-oriented programming. Yeah, so the closest analog to a type class in, for example, Java or C# would be an interface, or again in Rust, a trait. Yeah, and an instance of a type class in, for example, Lean would then correspond to like the piece of code that implements your particular interface in Java. The cool thing about type classes that is not possible with interfaces in Java is that you can define instances of type classes for a type that the author of the type doesn't have access to or didn't think about. So you can just define your own type class and then you can define an instance of that type class for any type, even for like the standard library strings, for example, and then you can sort of, for example, add a method to any type that you want in a totally safe way. That's also works with, yeah, That's why I said it's very similar to traits in Rust, because in Rust you can literally do that. For example, in Rust, if I define a trait foo that has a foo method, then I can implement foo for like the standard string type or the string reference type in Rust. And yeah, this way I can just add methods to types that I didn't even define or that I don't have control over, which in Java, at least when I was still coding in Java, was not possible to add a method to a type. You had to have like access to, yeah, the source code or like change the code literal definition of that type, which is obviously difficult if it's a standard library type or some external dependency type. Yeah, so I think this is a really cool feature. Okay, chapter 3.1, positive numbers. Okay, so in this chapter, I guess we're going to make a data type that only supports positive numbers, so natural numbers that are greater than 0. And the example they give is, for example, you could use that for representing a position in a file, as in like a line and column number. And obviously, usually you would like just use a unsigned integer for that. And well, either redefine the meaning of line and column numbers, that they just start at 0 and then maybe in the printing code like add 1 to each, or you would have like assertions in your code to make sure that you're not using 0. But obviously you can also make your own type with what we do here. So we have this inductive data type where the base case is the number 1 and then there's a successor function. Well, that essentially is, yeah, it's like the +1 function. So using this type, obviously it's impossible to construct a number 0. And obviously this is the same as the inductive definition of the natural numbers, except that it starts at 1 instead of at 0. But I mean, with our own type now, we suddenly cannot use numeric literals. I mean, it's not like the compiler can magically figure out what we mean if we assign like the numeric literal 7 to our position type. So instead, we would have to write it in this sort of unary way of just calling the suck function 6 times. And obviously the same is true for addition and multiplication operators. We didn't define any instances for those for our own type. Yeah, whenever Lean gives this error failed to synthesize, that essentially means that there's an overloaded operation that we didn't implement for our particular type classes and instances. Okay, and the way we're gonna solve this problem from the previous section is using type classes, and essentially they are like a more powerful version of interfaces. So they just define a collection of methods. And when we say methods in this context, we don't mean a method in the object-oriented sense, that it is something that has access to like the private state of an object. The method in this case is just terminology for overloadable functions. So for example, we could define a type class plus that has a method plus that allows us to add two numbers. And would look like this, like class plus of a type alpha, where there's a method plus that takes 2 alphas and returns an alpha. And internally, type classes are basically just another kind of type, and the type, for example, of plus is then a function from type to type, because it takes a type alpha as an argument, and you can think of it as like returning another type that then describes the implementation of the type class for alpha. Yeah, so I guess it's called add in the standard library, and here we see that the type of add is a function from types in a particular universe to another type in the same universe. What's a bit confusing to me is that like the way I read this signature is that if we have like type, we have like add and we give it a type in the hierarchy level 11, then it should give us a type in the same hierarchy level. But if I try this, I get that add of type 11 is of type 12. But I think, yeah, that's probably because like if you think on the value level, then it's going to give you a type 11, and the type of type 11 is obviously going to be type 12. So I guess makes sense. Yeah, and to define an overload for our function, now we create an instance. So for example, instance of plus for the natural numbers, where we define the plus operation to be just addition. And this colon here is supposed to symbolize that plus nat is actually a type, and we are defining a value of that type, so an instance of that type. And I guess the compiler has to enforce somehow that these are unique, because I mean would be very bad if we could define a second instance where suddenly plus is the subtraction operation. And I guess in memory or in the internal representation, such an instance is just like a dictionary of the methods on as keys and sort of function pointers basically as values. Okay, so and if you create a type class, Lean will automatically create a namespace for it. So that's why we can call it like this as plus.plus. And if we then open that namespace, we don't have to specify it anymore, so we can just call it as plus instead of plus.plus. And I think we also haven't seen this syntax before, where we open a namespace, but we import essentially only one method from that namespace, so only the plus method here. And we can now define a plus function for our own position type by just pattern matching on it, like the same way it works for the natural numbers, and then create an instance of the plus class for the position type. And yeah, then we can compute 7 plus 7. Overloaded addition. Okay, and so the built-in plus operator in Lean apparently is syntactic sugar for a class called hadd, which is short for heterogeneous addition.
Heterogeneous
addition. And yeah, that means that we don't have to have the same type for the left and right operand. So we can, for example, add a natural number to a float. And actually, I think this is different from how it works in other languages. So I'm pretty sure that, for example, in C, addition is always homogeneous, and the way you can add like an int to a float in C is that it just promotes the less general type to the more general type. So it will essentially then, I don't know if the compiler does it automatically, but it's gonna cast your int to a float. Okay, yeah, it happens automatically, but the way, as far as I know, it works internally is that, it's going to cast b to a float here. Yeah, and then there's another type class that we already saw called add that requires that both of the arguments are the same type, and that will then also be found when the compiler is searching for an instance of hadd. So I guess we should be able to use it with the plus operator as well, if we just define add. Yeah, and if we create this instance here, then we can write 7 plus 7 with our own position type, and it just works. Conversion to strings. Yeah, and there's another type class called toString, where we can just convert values to strings that we can, for example, print them. So we can define this function post toString, which takes a boolean that indicates whether we are at the top level, and then a position number, and gives us a string. And if we're at the top, we don't need parentheses, otherwise we parenthesize. By the way, if you wanna try any of this stuff without installing Lean, you can go to live.leanlang.org and just use it in the browser. And what I'm a bit confused here is that we're defining here a local function using let. I'm still not exactly sure when we need let and when we need def, okay, so I guess we just cannot use def inside of expressions, but with let it works. Yeah, so if we move it outside of the function, then obviously at top is not defined, but it's not complaining about the def. And also seems like it's not going to infer the argument types if it's defined using def, but when we put it back to a let, we don't need to define the type here. Interesting. Okay, so we match p, and if it's 1, we print post.1, and otherwise we call this parent function and use string interpolation, and we make the recursive call inside of the string. And yeah, definitely works. Okay, and we can then create a toString instance by just calling post toString with true. And then it knows, even like when we do a string interpolation like this, to use our own toString method. And obviously the output is like unnecessarily long. Would be much better if we just printed a base 10 number. So I guess we can convert it to a natural number and then use the toString of the natural number. And the interesting thing to me here is that it's not complaining that I'm defining two instances of toString for pos. So apparently you can just like overwrite these instances. And that's something that's actually a bit weird because, for example, in Rust, that's not allowed. It's then gonna complain that you have conflicting definitions. And I'm also wondering why we're calling toString like this here instead of saying dot to string. Apparently we cannot use the dot syntax in here. Yeah, so even if I open the toString class or namespace, it doesn't allow me to call it using this like dot accessor syntax. Interesting. Yeah, they also write it here when we have more than one instance, it literally just takes the most recent one, which seems like it could lead to bugs if you can just redefine an instance. And I guess hashtag eval is going to use the toString instance if there is no wrapper instance. Overloaded multiplication. Yeah, for multiplication we have this class hmul that will allow us to multiply different types. And like in addition, there's also this class mul that is used when the types are homogeneous. And if we do this, we can use the multiplication operator. Literal numbers. Yeah, so what we still cannot do with our own number type is writing like a literal, like 27. And one way we could do it is to write a conversion function from natural numbers to our own type. And I mean, one downside of this is that not every natural number is a valid position, so 0 is invalid, so we would have to return an option from that function. And yeah, if we had to explicitly convert it each time, then it would be very inconvenient to use our own number type. Okay, and to work around this problem, Lean gives us 3 type classes. One is 0 and the other one is 1, and then there's one of nut. And 0 will literally just allow you to define a 0 value that the number 0 can be converted into. And since we don't have a 0 value, I guess we are not going to define that. And yeah, for the number 1 there is the class 1 that works. If we try 0, it doesn't work. We try 25, it also doesn't work. And then we have this class of nut, which takes a type and I guess a natural number, which I don't know why it's using an underscore for a name here, and then gives us a value of the type. And it's at this point not quite understandable to me why we put the natural number in the type instead of as an argument to this method here. Yeah, this unnamed nut argument is then going to be the actual literal number. Okay, and I guess because we have it as part of the type, that makes it possible to define instances only for the numbers where it makes sense. So if it was part of the method here as an argument, then we would need to define it for each natural number, I guess. Yeah, and this, I mean, essentially is one of the more special features of Lean is that it allows these sort of dependent types where you just have a value, like a natural number, as part of the type. And I mean, other languages like Rust or C++ do something a bit similar. They have a thing called const generics, or at least in Rust it's called const generics. But my understanding is that dependent types are still a bit more general and powerful than const generics. Yeah, and this kind of flexibility allows us to provide instances not only for particular types, but also restricted to particular values. And we're going to do an example here where we have a type less than 4 that represents the numbers from 0 to 3, just as an enumeration. And obviously we don't want to be able to write the literal 27 and convert it to this LT4 type, but 0, 1, 2, and 3 should work. So we can literally specify these instances separately by just writing the literal as part of the instance and then giving the corresponding number. But I mean, obviously this would get very tedious for our type that has an infinite number of numbers, our positive number type. And yeah, if we do it like that, we cannot write the number 4 as an LT4 instance. Okay, and for our positive number type. Obviously, for any natural number n plus 1 it works, because with n it's 0, it's going to be 1, and yeah, I mean n plus 1 for a natural number n is never going to be 0. And let's see how this definition works. Okay, so we can now create the number 25, but this looks a bit confusing to me, because we literally have an expression essentially as the type here. But I think this is probably some kind of syntactic sugar. Let's see if this also works if we do 1 plus n. So yeah, that actually works. Interesting. So apparently we can literally just write some arbitrary expression here. But what if we do like 10? I mean, it's not complaining about our function or instance definition itself, but 25 no longer works. And even if we write 1 plus n, I mean, it's still working in the instance here, but we can no longer synthesize positive for the 25. So I guess in the end it is some kind of syntactic sugar for saying like not.suck n, because that works, but 1 plus n does not work. Yeah. Okay, we have a recursive let that will convert us a natural number to the corresponding positive number, but like adding 1, so 0 becomes 1. And then we call that with the number n that we did not get as an argument, but as a part of the type itself. Yeah, very interesting stuff. And now we can write 8 as a literal, but not, for example, 0. Exercises. Another representation. Okay, so they're saying we could have defined it as a struct that essentially contains a natural number, and the value is defined to be that number plus 1. And let's see. I mean, first of all, we have to call it something else, but okay. Yeah, so if we do suck 25, then we get this instance where the pred is 25. Let's try making a instance of add. Okay, maybe it will work like this if we just add the predecessors. And for some reason this is giving 5, which doesn't make sense to me at all. Okay, but if we do it like this, it doesn't work, so I guess we have to add 1 here. So we get the number 2 essentially. Okay, let's do multiplication. I think this could work, so we take the literal value of them, multiply it, and then do minus 1, because yeah, then we take the successor to construct our positive number. And this gives us 4. Let's try to string. Yeah, that also is working, so we just use the toString of the natural numbers. Okay, and the tricky one is maybe going to be off nut, because again I think we can only do m plus 1, and we are going to have to just give n as the predecessor, I guess. So let's try this. Yeah, I don't know why we need parentheses here, but we can convert 27 to a plus 2, but 0 is not working. Nice. Even numbers. Define a data type that represents only even numbers. Okay, and I guess we haven't learned yet how to do a off nut of this kind of data type, but I would say we can represent it like we did with our plus2, where we just use a natural number that is the half of it, and I mean, if it has a half that's a natural number, then it's even. And I guess that we cannot just, do essentially this where we do n star times 2, and then we get that the half is n. I mean, weirdly it doesn't complain, but let's check eval 20. Oops. And yeah, this does not work for some reason. Yeah, we cannot call it. We cannot do the naive thing. Yeah, really wonder how we could achieve this. So I don't think I'm going to do all instances, but let's try doing toString. We should be able to just do it like this, and let's see, does it work if we just add a.half to b.half? Okay, let's do 6 plus 2 and we get 8. Yes, that's working. And I guess for multiplication going to be similar. So if we do times 2 here and times 2 here and then divide it by 2, yeah, so essentially we can just do it like this. That should work. 12, yeah. HTTP requests. Okay, so well, obviously an HTTP request starts with like the method, like get or post, and then a URI and then an HTTP version. Okay, that seems like a larger exercise. Guess we have a post where we have a URI and okay, I guess I'm a bit too stupid here. Okay, so we have to define it like a function, like with this syntax, okay. I mean, so if we wanted to do it properly, we would have to do headers here and a string, I guess, or I mean, a sequence of bytes. And I mean, we didn't define headers, so I'm just going to use like a normal string for the body. And for the post, we get a body, and for the get, we don't. And then we have a response where we are just going to have a version, a status, which is a natural number. Okay, it's a bit more complicated. Or is it? Not really, because the text is determined by the natural numbers, so it's literally just like this. And then we could have, I guess, okay, we need to find, apparently we cannot derive wrapper for this type, I guess because the other types don't have it. So, and we do a response. If we get a post with a particular URI version and body, I would just say we do a response that is going to get the same version and okay status. And I don't get why it is complaining. URI version body. URI version body. We give a HTTP response. I guess I need to specify the namespace here. We give it a version and a status and a body, and it complains. Okay, so somehow it works if I use the explicit match syntax, and I don't get it. Why is it not working with this abbreviated syntax? Maybe the abbreviated one we are not allowed to name it, I guess. So if we just do serve request to response and remove this, then yes, it works. Nice. So let's check. We just made a very stupid echo server, or I guess a simulation of an echo server. And I'm going to try open. We're going to do this, and it gives us a response like this. And I guess we should have a toString. I think I'm only going to do the response. Let's see. So I guess we cannot pattern match here, or somehow this is ambiguous. Okay, but version status don't want to get replaced. How do I do a new line? So let's imagine we were not too lazy to add headers, then our body would have, I guess, and somehow we cannot pattern match here. Okay. Well, it does look somewhat correct. I guess you don't need double new lines here. Okay, well, it does indeed print something. Let's see our serve. Okay, let's try that it works for post. Then we need to give it a body of, yeah, we evaluate it, we see echo this, yeah. Okay, I don't know if this is what the exercise was intended to do, but now we have a bunch of boilerplate code for a very bad implementation of a subset of HTTP. Anyway, type classes and polymorphism. Okay, the way we write polymorphic functions that take a type that implements a certain type class is apparently with these square brackets, which is kind of different from how I know it from other languages, because in Haskell, for example, you would write that it implements show, which is like toString, I guess, as sort of a constraint for the actual type, which is a toString. And I mean, in Rust as well, you would write it like sort of using this angle bracket syntax, like before the actual argument types as sort of a constraint. So kind of interesting to see the syntax here. This sort of almost expresses how it would work internally, that you get, I mean, like literally passed a dictionary that has all the function pointers that you need for your particular instances. Maybe that's why they chose that syntax. Checking polymorphic functions types. Yeah, if we try this, we just get a kind of cryptic type, which gives us a weird like type hole and then IO of unit. And I guess this meta variable indicates that Lean tried to infer the implicit arguments, but sort of failed to do it. And if you want to suppress that, you can apparently use the add character, and that is then going to literally print the type, which I guess it would also just do if you left out the parentheses. Yeah. Defining polymorphic functions with instance implicits. Okay, if we do a function that will sum a list, we need an instance add for the type, we need of not with 0 for the type, and then a list of that type, and we can use 0 for the empty list, and otherwise just use the plus operator to sum all of the elements. And I wonder, I thought that we can also do this, yeah, instead of not 0, we can literally just use 0 here. And yes, yeah, literally the next paragraph says that we can use 0, and yeah, the function works as expected, but it does not work for positive numbers because obviously we don't have 0. And obviously this is also included in the standard library, so if you just call .sum on a list, it will be this function. Yeah, and for these instance implicits, yeah, I mean, the way the instances work is essentially it's like a structure that has a field for each method that is defined in the instance, and the Lean compiler will then find this instance value and pass it to your function that takes an instance implicit at the call side. And the technique for finding instance implicit is different from the other implicit arguments. So normally we learned already we can do implicit arguments with this curly brace syntax, in which case Lean will use a technique called unification to find a argument value. And that unification process is, I guess, local to the call side, so it uses the types that can be inferred at the call side. And for instance implicits, the compiler just has a table of instance values that the programmer defined, and it's going to search through that, I guess. And we can also use these instance implicits to define instances for our own polymorphic types. So in the previous chapter we had this polymorphic point type, which is parameterized by a type alpha. And if we want to write an add instance for it, obviously we need to require that there is an add instance for alpha. So we can define that before the colon as an instance implicit. And the way this is going to be stored is that if we have add of polymorphic point of nut, then the instance of add nut is, or a reference to the instance of add nut is going to be stored with that add instance that uses it. And yeah, this makes type classes very powerful because you can use them as like building blocks, and the compiler will put together the correct instances if you give it the desired type. Yeah, so it's like a request to the compiler to assemble the necessary helper functions behind the scenes, so you don't have to pass this kind of stuff explicitly, which I guess could be used to make some very interesting APIs, methods, and implicit arguments. And so the way my type class instance is going to work internally is that it's going to construct a structure that contains the implementation of each overloaded method and a namespace with the same name as the type class. And for each method, there's going to be a function in the class's namespace that retrieves the implementation from an instance. And this is why I guess the type of offNut.offNut takes an implicit type alpha, it takes a natural number, it takes an instance of the type class of nut for that alpha and that number, and then gives you an alpha, which is different from the type that we were using to declare our instances, because in the declaration of the instance, the type is literally just alpha, just a supplied type. And I guess that sort of transformation of that one type to the other type happens by the compiler automatically, because the declaration here in the standard library also just declares its type as alpha. Yeah, so it's analogous to the way that when you create a structure, then the compiler also creates accessor functions to access the fields. And the difference is that the structure's accessor is going to take the structure as an explicit parameter, and the type class method will take the type class instance as an implicit argument here. And for Lean to be able to find the instance, it first needs to know the parameters. So this is why we first have an implicit argument alpha here that Lean has to find the type, and then it has to find the corresponding add instance for that alpha. And in the offNut case, this is a bit different because we have this type alpha here, which is implicit, but the literal value n cannot really be implicit, so then it sort of turns that into an explicit argument here using the normal parentheses syntax. Exercises, even number literals. Write an instance of offNut for the even number data type from the previous section's exercises that uses recursive instance search. I have no clue how we are going to do that, but let's try. I mean, we can do one for 0, but what if we do... Well, if we do, we have an offNut for even of n, then we can get an offNut for even of, well, 2n to n plus n. Like, this is what I would think about, but I don't know if this is going to work. That seems a bit crazy. And I guess at least then we also need one for 1, right? We need one for 2, I mean. Because what if I do eval 2 of nut should now work, right? 2 with nut. But what about 4? Recursive instance search depth. There is a limit to how many times the Lean compiler will attempt recursive instance search. Yeah, I mean, obviously. Experimentally determine what the limit is. Well, we can... I was doing the wrong type, so I guess this sort of naive approach is not working. It's working with 2, it's not working with 4. I guess if we could do it like this, so if n is even, then n plus 2 is even. Yeah, I mean, obviously that's the correct way to do it. And with n plus 2, yeah, it's somehow able to search this sort of thing in reverse, where it then subtracts the 2 and finds the instance, or base case instance. The question is, does it work with 10? Yeah. 2 to the power 4 is not working. Wait, why not? 8, 16, 256. Yeah, our instance here actually is wrong because we need to have, we know that n is even, so we need n plus 2 divided by 2. And okay, now it's actually giving us the correct number. If we try to print it as a string, yeah, it's working. But I really wonder what, okay, the limit seems to be not that large. 1000 is not working. 500 is not working. 300 is not working. We saw 256, 58 already doesn't work. And so the question is for 256, what's the largest, or like what's the number of reductions that we need to do here? Essentially 128, I guess, because each time it's subtracting 2, so I guess 128 is the limit that we're supposed to find in this next exercise. Yeah, I really wish it had solutions for this stuff, but I couldn't find the solutions. If someone knows where the solutions for this book are, please tell me. Controlling instance search. Yeah, we already saw this add class, but that required that both of its arguments have exactly the same type. And sometimes I guess we want to add different types of things. For example, a natural number and a positive number. And I mean, we can define our own functions for that, but they cannot be used with the add type class. Heterogeneous overloading. And that's where this type class hadd comes in. And yeah, then we can create an instance of hadd and then define the type of both arguments and also the type of the result. So adding a natural number to a positive number will yield another positive number. And if we define these instances, then we can suddenly use the plus operator for adding positives and naturals. And I guess they're defining a simplified version of hadd here called h plus, which takes an explicit type alpha, beta, and gamma. But if we do it like this, then we cannot use it in the same way as hadd, because actually I don't know why, but somehow this is not working. And the compiler is complaining about some meta variable, which is to say there's a part of the program which it could not infer. Okay, and the reason is, so we have this h plus instance, which is defined for not a pos and another pos, but the compiler doesn't know that we are expecting a pos here. For example, there could also be an h plus instance for not and pos and string. Right, and that would also be valid there. So I guess if you explicitly specified that you want to get a pos back, then it should work. Yeah, that's what they are doing next. So they're just giving explicit type annotation here and then it works. But obviously that's not very convenient. Output parameters. And we can solve this by declaring gamma to be an output parameter. And that is going to mean that I guess the type class instance search algorithm is going to treat it different from the other parameters. Yeah, and the output is just going to be a parameter that's not going to be needed to be known to search for a type class. And we're going to do that by using this out param thing. I don't think it's a keyword. Don't know exactly what it is, but it says it's a gadget, whatever a gadget is. Yeah, and with that it works. Okay, and apparently you can think of this as giving the compiler a function to determine the output given the inputs. So given h plus and pos and not, it can then determine that the output of this has to be pos. Yeah, and obviously this sort of overloading with type classes is a lot more powerful than the simple overloading in Java. I mean, one thing that we already saw it can do is you can overload based on the return value of a function, which I think you cannot in Java. Default instances. Yeah, so we already saw we can get lean to search for instances, even if the output parameter is not yet known, just by knowing the input parameter, but sometimes we want to search even if not even all the input parameters are known. And the way we do this is by, I guess, defining default values for those inputs. Yeah, and there's this thing called default instances where that are going to be available for instance search even when not all their inputs are known. Yeah, you can also create unexpected behavior with that. So I guess it's something to be used sparingly because yeah, if the compiler is going to pick the wrong instance because you declared it as default, yeah, that could be confusing to debug. And yeah, one example with a default instance here is that if there is an instance for add alpha, then we can derive an instance for h plus with yeah alpha 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 as the types. I guess the analog in a normal programming language like Rust would be some sort of like blanket implementation of a trait. So if you have this trait bar and we say for every t that has implemented foo, we can implement bar by essentially calling foo. I guess yeah, that's what this kind of syntax is doing. And with this instance, we can, well, call it if we have two arguments. But if you have only one argument, it's going to complain that it doesn't know the second one. And I guess the goal here would be to then just have it assume by default that the second argument is also going to be a natural number. And that works by using this default instance syntax, which will yeah cause it to use that syntax by default, that instance by default if it matches so far, I guess. And yeah, what this will do is in places where we expect a heterogeneous instance, it will, if we only supply one argument, it will just default to the homogeneous instance. Yeah, and that's also how the literals default to natural numbers, because if you just write a 5, I mean, technically could be anything that implements off nat, but the default instance is the one with that gives you a natural number, then yeah, if you just write 5, its type will be inferred as natural number. And apparently you can also prioritize these default instances. So if there are multiple that apply to, like, yeah, make sure it picks the correct one. Exercises. Okay, we should define a heterogeneous multiplication for the p-point. Let's get the definition here. We want an instance like this. And I guess what we want is, it's confusing to call this x. It's called hmal. And of course we cannot synthesize the multiplication here because we need to give it an instance implicit for what? I guess just would be enough to give it a multiply for alpha. And indeed it appears to work. Arrays and indexing. Yeah, in this interlude it is described that we can use like the normal array indexing syntax that essentially every programming language uses to index a list, and apparently this also works using type classes. And in Lean there's an array type, so in addition to the list type, I guess, and that array type is going to be like a contiguous section of memory that's going to dynamically resize like a vector in Rust or C++. And obviously that's much more efficient like for the CPU cache. And yeah, I mean, literally you don't need an indirection to look up each element, and so you can look up values in constant time. But obviously in Lean these are going to have to be immutable, because yeah, otherwise it would sort of destroy the guarantees of our referential transparency, I guess. And so to modify it, you need to like create a copy of the array. But the Lean compiler has an interesting optimization here, where if it can detect that the reference count is 1 of the array, then it will modify it in place instead of making a copy. And the syntax for an array is just like a list, but with a leading hashtag symbol. Yeah, and the interesting thing in Lean here is that for this index syntax to work, the compiler needs a proof that the index is valid, so that it can verify at compile time that it will not crash. And I think most of the time that proof is going to be inferred, but you can also supply it manually in the complicated cases. Non-empty lists. Yeah, we can define a non-empty list like that with a head alpha and a tail that is a list of alpha. And I guess we can now define an index accessor for this structure. If it's 0, it should obviously just return the head, and if it's n+1, it should return the nth element of the tail. I guess if the tail is non-empty. And we define this get question mark function here. which takes a non-empty list and a natural number and returns an option of alpha. And if the natural number is 0, we just return the head. And otherwise, if the tail is empty and we have a non-zero number, then we return none. And if the tail has a head, then we call the function recursively on the tail of the tail with essentially n plus 1 minus 1, so n. And obviously, a way easier way to write this is to just use the indexing operator. If you put like a question mark after it, it will give you an option when the index, like a non-value when the index doesn't exist. And okay, we can write this abbreviation for a proof that the non-empty list has a certain index, which is just going to be true if it's less than the tail's length. And there's this decide tactic in Lean that was introduced in the interlude that I skipped over. That's just going to, like in this case, evaluate the length and check that it is at least 2. Yeah, and with this sort of definition of this inbounds proposition, we can write a get function that doesn't need to return an option. So we take our non-empty list, we take our index, and we take our proof that the index is in bounds. And then we can call this normal indexing operator, and I guess Lean will automatically supply the proof to the operator that it is in bounds, because we're not passing it explicitly. Overloading indexing. And we can define our own indexable types using this getLM type class, which will take 4 parameters: the type of the collection, type of the index, type of the elements that are extracted from the collection, and a function that determines what counts as evidence that the index is in bounds. So we have class getElement, collection type, index type, item type, which is an output parameter, in bounds, which is also an output parameter that takes the collection type, the index type, and gives a proposition. Okay, let's define that. They define now an instance of getElem for our non-empty list, where we just use the inbounds function as the proposition, and just use the get function that we defined earlier as getElem. Yeah, and if we now evaluate Idaho spiders at index 9, we get a compile time error. And this type class then also gives us the flexibility to use new types as an index to existing collections. So we can define a getElem for the normal standard list type that works with our positive number type. And the proposition is then going to be that given a list and a natural number, or a positive number, sorry, the list length needs to be greater than our positive number. And we just define the getElem by using the index notation with our positive number converted to a natural number. And it doesn't even need to be a numeric type. For example, here we can define getElem with a polymorphic point and a boolean. And the proposition that we use here is going to be always true. And then we just decide whether we want to return X or Y. Standard classes. Yeah, and all the operators in Lean correspond to some type class, and it's not like in C++ where like you use literally the ASCII character of the operator to overload it, but they always also have some like normal name, like hadd for the plus operator. Arithmetic. Yeah, and all the arithmetic operators, there's a heterogeneous and a homogeneous implementation available, like for hadd and add, except for the unary minus bitwise operators. Okay, and it's using a very weird syntax for the bitwise and, because it's using a triple ampersand sign, but I guess you don't need it that often anyway. Yeah, so we can do 5 and 4 or XOR, or take a complement. Maybe we need to put in parentheses. I don't really know how to call a complement. Maybe we need to specify the type explicitly, like, then it works. I wonder if it ever makes sense to have like an XOR implementation where X and Y are different types, but I guess it's at least possible. Equality and ordering. So for equality, we're going to be using this BEQ class, Boolean valued equality. And I guess this is a bit complex because Lean also is a theorem prover, so there's two different types of equality. And Boolean equality is normal equality that we are used to from, for example, Python, that just takes two things and returns true if they are the same. And we don't have this complexity of for example, differentiating like in Java between equals and like equals the method and comparing using two equal signs, because Lean is so high level that we cannot directly observe pointers. So we only have like the value equality, not the reference equality. And okay, then there's propositional equality, and that is going to be then just a mathematical proof that two things are equal. So that's written with a single equal sign, and it's going to give you a type that certifies that these things are mathematically equal. And for example, with the Boolean equality, we can obviously compare like strings, but we cannot compare functions because, wait, I think it's undecidable if two arbitrary functions are the same function. Yeah, and propositional equality is going to be more like a type, because a mathematical proposition is like a type that describes the evidence for some statement. And obviously, yeah, we cannot automatically check for propositional equality. And if we write like this statement, like the function from x to x plus 1 is equal to the successor function on the natural numbers, then this is just like a statement, or a type rather. It's not an invocation of some code that will check that equality. Yeah, and we could obviously then write a proof for this sort of statement. And since we are mainly concerned with using Lean as a programming language in this book, yeah, most of the time we're going to be using the Boolean equality, not the propositional equality. Yeah, and obviously if the proposition is decidable, the equality proposition, and decidable just means that there is an algorithm that returns true or false depending on whether it's true or false, then we can sort of convert the propositional equality to a Boolean equality. But yeah, for arbitrary functions, definitely not decidable, I think. And the if syntax in Lean works with decidable propositions. So 2 smaller than 4 is a proposition, which is to say like the type of 2 smaller than 4 is not a Boolean like it would be in almost any other programming language. So the type is a proposition. And I'm still not exactly sure what the difference between a proposition and a type is, but so it says prop is a type, but I think it's somehow built into the language because I cannot go to definition here. Yeah, obviously not all propositions are decidable, otherwise, yeah, we wouldn't need like mathematicians. And the way Lean can determine if a proposition is decidable is that it's using a type class, which contains the decision procedure. Okay, and these sort of less than, and equal operators are also just defined in type classes. And interesting to me that they have, I wonder if there's like a default implementation, like if you have a less than instance and if you have a equality instance, or like a decidable equality, that it automatically implements it or something. Yeah, and the easiest way to define instances would be in terms of existing instances. So less than for our positive numbers can just be defined in terms of less than for the natural numbers. And apparently if we declare them like that, they're not going to be decidable. So we need to declare an instance of decidable for x smaller than y, which will then fall back to the decidable instance of the natural numbers. And I mean, obviously we have duplicated code here because we define the less than twice, once for the normal instance and once for the decidable instance, but apparently at least the compiler checks that they are matching. Yeah, and obviously if you want to write code that checks whether something is less than or equal or greater than, that can be inefficient if you call those separately, because then you have to evaluate 3 separate functions. And the way this is solved in Java or C# is that there is a compare to function that implements all operations at the same time. I'm just going to return like a negative integer or 0 or positive integer to indicate less than, equal, and greater. And obviously, I mean, that's kind of a hack to encode that in integers. So in Lean, there's an inductive type ordering that has less than, equal, and greater than. And then we can define our comparison function from positive numbers that to yield an ordering as the result. And we can define an instance of the ord type class using this method, hashing. So in Lean there is a hashable type class that will hash a type to a uint64. And actually that honestly seems a bit limiting, because what if in the future we want to hash to not 64 bits but 128 bits or something. So in Rust I think I kind of like how they do it. There's this hash trait that you can implement, and the way you implement it is just you feed all of your data to this hasher that is passed to you, and then there can be different hashers. I guess in Rust also the finish method then just is hard-coded to return a 64-bit number. So I guess it's the same, but still very flexible because you can have different types of hashers. And the hash function needs to be such that if the two values are equal, then obviously they need to hash to the same value. And if they're not equal, then, well, obviously there is going to be hash collision, so they could still hash to the same value, but they should hash to a different value. So we can define a hash for our positive numbers by hashing just 1 to 0 and using mix hash with a recursive call to hash bigger numbers. So I wonder why we don't just use convert it to a natural number and then convert that to an int64. And obviously we can use these implicit instance arguments if we have a parameterized type. So hashing a non-empty list can be done if the elements are hashable, and then we can just mix them by hashing the head and the tail. And the next example is a binary tree where apparently the leaves are empty, I guess, and we only have values inside of the inner nodes, and we just recurse through it to compare the equality. Obviously, given that there's a Boolean equality for alpha, and we can also write a recursive algorithm to use mix hash to create a hash value for the binary tree. Deriving standard classes. Yeah, we already have seen that Lean sometimes can derive classes on its own using this deriving syntax. And it's also interesting that we can apparently use a standalone deriving command if for a type that has already been defined. So I guess we don't need to modify the declaration of the type. We can just write it anywhere. I'm using this deriving instance for syntax. And the instances that we saw above, like Boolean equality and hashable, can in fact be derived automatically. So we can derive instances for inhabited, for Boolean equality, for wrapper, for hashable, and for ordering. And obviously if the derived instance is not what we want, like for the ordering, then we have to write it by hand. Yeah, and obviously if it's possible to use this deriving syntax, then it's good to use it because it makes the code more maintainable, because we can change the type and the derived implementation will automatically change in the correct way. Appending. Okay, there's a heterogeneous append class which can append an alpha to a beta to get a gamma, and the syntax is going to be using the double plus operator. And for example, we can define an instance for append for our non-empty list, where we just take the head of the first list and then the tail of the first list, and then we append that to the head of the second list, const with the tail of the second list. And obviously we can do the heterogeneous version where we append a non-empty list to a normal list to get a non-empty list. Functors. So functor is essentially just a mappable type, so it has a map function that can essentially usually, for example, a collection type for a type alpha that has that can take a function that goes from alpha to beta and then becomes a collection of type beta. Yeah, for example, the functor instance for option would leave none untouched and call our supplied function f if it's a sum option. Yeah, so obviously for a list, functor.map is just going to be called on every element of the list. And obviously on option, it's going to be called if it's sum. And yeah, obviously for a list of lists, then it's going to be called on each element list. And Lean also has an ASCII operator for the map operation just because it's so common. So you can use this $sign in angle brackets to call functor.map. And to define an instance of the functor type class, we just need to define a map function that takes a function f and our instance of the type. And for the non-empty list, for example, we can map the head and we can also map the tail. Yeah, and we are giving the functor here, we are giving it non-empty list, which is essentially a function from type to type. So it takes the type alpha and gives us a type. We are not directly supplying functor with a type. And I mean, this is because a functor is supposed to work for no matter how you parameterize the type. So if we were able to specify the type here, we could just have a map that only works for non-empty lists of integers, but not non-empty lists of strings, for example. Yeah, obviously for the polymorphic point, we can also do this by just mapping the x and y values using the function f. Yeah, and the mapping is always going to be applied to the outermost layer. So if we have a non-empty list of p points, then we're going to be mapping over the p points, not over the natural numbers that are inside. The same if we map over a list of lists, then yeah, we're only going to map over the outer layer. And in the definition of the functor class, it uses a language feature that we have not yet seen, which is default method definitions. And I mean, it uses this because sometimes there is a generic implementation for a method, but there's also for a particular type maybe a more efficient definition. So in the type class, you can specify the default implementation, then in the instance, you can like override it essentially. So in the functor class, there's this function map that doesn't have an implementation, but there's this function mapConst, and mapConst takes a type alpha and a type beta and a value x of type alpha, and our collection, which is the functor with beta values, and it returns a functor with alpha values, and it's going to do this by just mapping over the collection of the beta values with a constant function that always returns our x of type alpha. And I guess, well, this is fine as a default implementation, but if you have a concrete type, maybe you can come up with a more efficient implementation of this for your type. And obviously, you could write an invalid functor instance, like if you write a functor instance for a list, you could just always return the empty list. Or for a p point, you could maybe map over x and not over y, or just like swap x and y. And like to prevent that, our functor instances should follow two rules, which is that mapping the identity function should not change the arguments, so should return, like if you map the ID over a list, then you should get the same list, for example. And mapping two composed functions should have the same effect as composing their mapping, which is to say, I guess that, I mean, let's write this out. This is a bit confusing. So we have mapping two composed functions should have the same effect composing their mappings. So I guess mapping like f composed with g should be the same as map f composed with map g, so that we have this sort of like distribution law. I think this is what it means. Yeah, so ID mapped over x equals x, and the second rule says that map of a function that takes a y and applies f of g of y over x equals map f of map g of x. Yeah, and we can write the composition using this little circle. So f circle g is f composed with g. Yeah, and using these two rules, it's already sufficient that we cannot really have a bad implementation that like deletes data or moves data around. Messages you may meet. Yeah, obviously we cannot derive automatically a toString, and the error message we're going to get is default handlers have not been implemented yet, and that just means, yeah, no one has specified a default way to implement toString, and I mean there probably isn't a good default way. Anyway, exercises: write an h, append list alpha, non-empty list alpha, and test. Okay, let's try. Okay, we have our x's, we have y's, and what do we want to do? So if x is empty, we're just going to have y, and if x is a non-empty list, then then what? Then we are going to have a head of x and a tail of h append of x's to our y's. I guess we need to define a variable rest, and now this is probably a non-empty list, and we have to do rest.head, rest.tail, maybe like this. Failed to synthesize. But why though? If I list alpha and a non-empty list alpha, a list of alpha, can we not call our own function recursively here? Yeah, somehow it was not allowing me to call happend recursively, but if I define it as an external function, it's not complaining. But okay, let's try, see that it works. And we get 1, 2, 3, 1, 2, 3. So I guess our implementation is working. Implement a functor for the binary tree. Okay, so we have our binary tree here. We want instance functor bin tree where. So if we get a branch, I would just say we need to create another branch where we, and I guess we're gonna run into the same problem as earlier, because let's see if we can call it recursively here. We need to do f of x and map of f of b2. And okay, but if we do functor.map, nope, doesn't want. So I'm gonna define it as another function, and we're going to define map equals bin tree.map where, okay, let's see, leaf stays a leaf and our branch gets map recursively. And why is this not working? Wrong syntax. Okay, so now if we do a tree dot branch 42, it's like this, and if we call this map with t1, why is it not working? It is working. We get 40. Okay, coercions. Yeah, so in programming languages usually you have a way to automatically cast values into a more general type. So for example, Java can automatically convert a byte to an int. And in Lean, yeah, this is done by a feature called coercions, and apparently you can extend this by defining your own coercions. Yeah, strings and paths. So for example, there's a coercion from string to file path, so you can just use a string instead of a file path. So for example, we're reading a file path f here in this example program, and just then calling io.fs.readFile on f without converting f to a system.file path. Positive numbers. So for example, we have this function pos.toNut that converts a positive number to natural numbers. And for example, we cannot call list.drop with our positive numbers right now because list.drop expects a natural number. But yeah, luckily there's this type class coi that we can use to coerce alpha into beta. So if we do an instance of coi for pos and nut, then by just calling toNut, then now we can call the drop function with a positive number. Chaining coercions. Okay, and Lean automatically can chain these coercions. So given this coercion to natural numbers, we can now also convert to integers, because pos.1 is then first coerced to a natural number and the natural number to an integer. And apparently it's smart enough to not get stuck if you define circular coercions. So we can coerce A to B and B to A and unit to A, and that gives us a way to go from unit to B, because we can first go to A and then from A to B. And Lean, for example, is able to coerce from alpha to option of alpha by just wrapping it with sum. So yeah, option is really similar to like a nullable in Kotlin, I guess. So in this list.last function, we see here that if the list contains one element, we just return that one element, and we don't need to explicitly call the option.sum constructor on it. It coerced automatically. And it can go several levels deep. So if you have an option of string, you can just write a literal string. Yeah, I guess in some cases it will not do that, so I'm not exactly sure. But here, if with the string, it created 3 levels of options for us, but if you do the same with a natural number, it won't do the same thing. And this is because we are using a polymorphic literal here, so if we specify the type of the literal, it will then wrap it properly in options. And you can manually insert a coercion with an up arrow. So I guess just to make it more explicit what's happening in the code. And apparently it's also necessary in some cases. But regardless, yeah, I think usually it's a good idea to make your intention clear. So non-empty list and dependent coercions. An instance of COE alpha beta makes sense when the type beta has a value that can represent each value from the type alpha. Yeah. So you can coerce from nut to int, but not from int to nut. Or you can coerce from a non-empty list to a normal list, but not the other way around. Okay, but apparently you can work around this by using something called dependent coercions. And those can be used when whether or not you can coerce or not depends on the actual value, which you can do with this COE-dep class, which takes a type alpha and a value x of alpha and a type beta, and then we can coerce to beta. And I wonder how this is then going to be like represented internally. So an instance of, or like this class internally has to be, I guess, a structure with a function that given alpha x and beta can give you the value of beta. So for example, here we create a COE-dep instance for list of alpha, which is our type alpha is list of alpha, and then our x here is a non-empty list, and our beta is the non-empty list of alpha, and we can coerce it to just using x for the head and x's for the tails. Coercing types. Okay, so in mathematics you often have these structures that consist of a set and some operations. So for example, in a monoid you have a set and you have a neutral element and you have a binary operation. And one way we could construct that in Lean would be we have a structure monoid where there's a carrier that's a type and a neutral element of type carrier and operation, a binary operation. And one instance of that would be the natural numbers with the multiplication operation that looks like a face. And the neutral element is then 1, but you can obviously have a different monoid on the natural numbers with addition and using 0 as the neutral element, and then it works for strings with the empty string and for lists with the empty list. And if we have a monoid, then we can define a fold map function that goes from a list to the carrier element, because for the empty list we can just use the neutral element. So we start this recursion here with the neutral element as the default, and obviously this first argument then is also going to serve as the accumulator. And if the list is not empty, then we use the operation with so far and with our function f that maps from alpha to the monoid carrier. It's a bit weird to me that they flip the order here, because we have essentially y comes first, but we apply it as the second argument here to our monoid operation. And if you want to just say like let a be a monoid and let x be an element of a, then you have to define a coercion from the monoid to its carrier set. And for that there's a COE sort type class, and honestly I still don't exactly know what a sort is, with the exception that the target of the coercion must be a sort. So a type or a proposition. So apparently like proposition is equivalent to sort 0, and type, which is type 0, is then going to be equivalent to sort 1. I still don't exactly get this concept. The term sort in Lean refers to these types that classify other types. Type classifies types that themselves classify data, and prop classifies proposition that themselves classify evidence or truth. Just as COE is checked when a type mismatch occurs, COE sort is used when something other than a sort is provided in a context where a sort would be expected. This is a bit over my head right now. But okay, we have COE sort instance with a monoid, and the output is going to be a type, so we can coerce our monoid into the monoid's carrier. And then we can easily rewrite the type signature of fold map to be, that f is just a function from alpha to the monoid, and the result is just the monoid here. Now, how does it know that this is now an element of the carrier rather than the whole monoid structure? Okay, and this also is the reason why we can use a Boolean expression as a proposition, because we can coerce from Boolean to proposition. And the proposition is just going to be that b is equal true. Coercing two functions. Okay, so often you have a data type that is a function with some extra information about it, for example, the function's name, and there is a type class coefun that can transform from non-function types to function types. So we go from a alpha to... Okay, I don't really understand this. So coefun takes two arguments. One is just a type alpha, and the other one is called make function type, which is an out parameter which goes from alpha to a type. And the result is then a function that takes an x type alpha and returns make function type, where the return type is make function type of x. Yeah, so the second parameter is a function that computes a type. Okay, so in this example here we have the structure adder that contains a natural number, which is how much to add, and we can have an adder of 5, but obviously we cannot call add5 as a function right now. But if we define our coefun instance, which will always yield the type nut to nut, and the instance contains this coi function which takes a alpha and returns an anonymous function that adds a natural number to alpha.howmuch, and now we can call it. Though I wonder why we need a separate type class for that. I guess it has to do with the fact that the type of the resulting function can actually change based on the actual value, which we couldn't do with the normal coi class. So if we have this sort of inductive JSON data type that defines all the possible valid JSON values, and then we have a serializer structure that consists of a contents type and a serialize function that goes from the contents type to JSON. Then for string, the contents type would be string and serialize would be JSON.string. And if we now wanted to call this str as a function, I mean right now it's a structure, then we would have to define a coefun instance. So coefun of a serializer is going to be a function that goes from contents to JSON, and here it depends on the actual value. And it's always just going to call the serialize method. So here we have a way to use it, for example. So we have this build response function which takes a string title and a serializer r and a record of type r.contents and produces JSON. And the JSON object it produces is just giving title, status, and our record serialized with our serializer aside JSON as string. So we're going to define a function to convert this inductive JSON type that we saw to a string. And I mean, JSON doesn't distinguish between floats and integers, which in my opinion is its biggest flaw. But to render it nicely, I guess we need to define a function that drops the unnecessary decimals in the toString of the float, which is just going to call drop right while the character is 0. And if we then don't have any decimal places anymore, then we can also drop the decimal point. Okay, and we need to define a function separate that allows us to, I guess, intersperse a string with a separator, such as like a comma. And we need to escape strings if we want to serialize them in JSON, because if the string, for example, contains a quote, then we need to escape the quote. And here we have a function that converts JSON to string, and it's declared as partial because it's too complicated for the Lean compiler to automatically prove that it terminates. But I mean, unless you want to use it in proofs, it's also not really an issue. And so true just goes to true, false to false, and so on. And for strings, we put the quotes around it and escape it. And numbers, we use our drop decimals. For an object, we use the name, the key in quotes, followed by a colon and a space. and calling string on the value. And then we map member to string over the actual members and separate that with commas and put it inside of curly braces. And then we can turn JSON into a string. Messages you may meet. This is what we already saw, that with these polymorphic number literals, sometimes you have to specify the type if you want it to get coerced correctly. Design considerations. Coercions are a powerful tool that should be used responsibly. Yeah, definitely. I mean, they can make your API very nice, but they can also make your program very confusing. Yeah, they repeat this famous quote from Structure and Interpretation of Computer Programs, for which I, by the way, also have a review on this channel. And I think it's a really good quote. Programs must be written for people to read and only incidentally for machines to execute. So yeah, you should, I mean, in some cases you just have to value performance more, but in most cases you should prefer to write readable code rather than write the code that is best for the computer, because unless it's called in a tight loop, probably correctness matters more than performance. Yeah, and the coercions are just a way of making your API use like the same sort of language that's used in the domain, like what we saw with the monoid coercion, because mathematicians sometimes treat a monoid just like a set. So it's useful to have that coercion if you want to talk about monoids in your code. So we have here our non-empty list, for example, and because non-empty lists can be coerced into normal lists, this sort of program works. We can call list.getLast, but if we don't provide an explicit type annotation, then the compiler cannot find the coercion. And I mean, sometimes it can result in confusing error messages. And apparently in Lean, if you use field accessor notation, it's not going to apply coercion. So there is definitely a visible difference between coercion and not in the API. So I guess another reason to not overuse it. Additional conveniences. Constructor syntax for instances. Yeah, so behind the scenes, as we already saw, a type class is like just a structure, and the type class instance is just a value of that structure. And obviously, I mean, there's some differences, because for type class instances, they're going to be stored in a table in the compiler and automatically searched, and obviously some additional information is stored. Okay, and I mean, we have these two syntaxes. So for structures, we would use the curly braces, and for type classes, we would use the where keyword. But apparently you can use these sort of interchangeably, so you can also create a structure with the where keyword, like instead of calling the constructor with these curly braces or with these angle brackets, you define it using the where keyword. That's actually interesting to know. So there's three ways, I guess. And if you have a type class like display, then you can also define instances using all three syntaxes, so using the angle bracket syntax and the curly brace syntax and the normal where syntax that we saw so far. Yeah, so depending on the context, you might use one or the other syntax. And this like normal assignment syntax for the instances can be useful if you have a custom function that returns an instance, for example. Yeah, examples. Yeah, so if you just want to try out some expressions while writing your code, you can use like this #eval and #check syntax. But sometimes it's also convenient to use this example keyword. Yeah, so it can also serve as a sort of documentation. You can even define an example that is of type function, even though it doesn't have a name, so you can never call it, but might show how to use your library. Summary. So we learned about type classes and overloading. Yeah, we learned that type class internally is a bit like a struct, and that we can create an instance of that type class. We learned that there's input parameters and output parameters. And we learned that we can also make default instances. We learned that most, or like all infix operators in Lean internally just call some method on a type class, so we can like override them. And this also includes the indexing operator, for example. We saw the functor type class, which is essentially like a mappable interface that allows you to specify a map operation for your type. We saw that the Lean compiler can automatically derive certain instances, and obviously not all classes are derivable, only if there's a generator that will generate the code necessary. And then finally we learned about coercions, which allow Lean to automatically convert types. And then there's a CoE-dep class that allows the coercion to depend on the concrete value, and the CoE-fun class, which allows coercing to a function where the function type also depends on the concrete value that we passed in. Okay, so that's it for today. Next time we will look at monads, and please let me know if you prefer this style like I did it today, with like just summarizing and maybe focusing more on examples and exercises, or if you want me to go back to reading word for word. Yeah, thank you for watching. Until the next one, hopefully.